Hello, my name is Gonzalo Abad, and in this tutorial I'm going to do a brief essay about electric technology in wind turbines. The contents of this presentation of this tutorial is divided into 6 parts. First of all, I will do a short explanation or definition of some concepts that we typically do not have very clear, and we mix all very often as well, which are techniques, science, technology, and philosophy. Then I will try to do an essay about philosophy of technique. Then, in general, I will speak about the need for models. And then in the third part, in this fourth part, I will be much more specific and I will do a short history related to the wind turbines. Then I will discuss about which could be the best electric technology in wind turbines. And finally, I will try to give some numbers related to the importance of technology. So let's go for the first part. Techniques, science, technology, and philosophy. I will not do very complex definitions or explanations. I will try to give an idea of what we understand about these concepts with just giving examples. And I will start with the science. What is science? Okay, I have to say that this first part, these first definitions, I will based on the philosophy of the Spanish philosopher Gustavo Bueno. So what do we understand about science? The typical examples are mathematics, physics, chemistry, biology, astronomy, etc. In general, we can say that they provide us universal truths, and this science maybe always are not oriented to obtain immediate practical use. For instance, in mathematics, we can develop some theorems and so on that we don't really see an immediate and a fast implementation into our real lives. Then, what do we understand about technique? In this case, I will, based on the definition given by this university professor of philosophy, David Alvar González, again Spanish. So the typical techniques examples are the potter, the blacksmith, the stone cutter, alfarero, herrero, cantero in Spanish, the architecture for centuries, the shipbuilding for many centuries, etc., and etc. In general, we can say that the techniques do not include scientific knowledge, so they don't use mathematics, physics, chemistry, etc., the truth given by these sciences. And the techniques, we could say that they are oriented to obtain an immediate practical use. In general, people say that first came in history of human being techniques, and then came the sciences. For instance, at the beginning, the necessity to work with numbers. For instance, in the States, to exchange elements like food and so on, and from that it appears the arithmetics. Then, for instance, the geometry came from the necessity to measure buildings, the necessity to measure lands, and so on and so on. Then, for instance, the chemistry started from metallurgy, from cooking, from the alchemy, and so on. The physics science, the origin is in the necessity to move mass, to know how much is the slope of one element in order to be able to move there from one car and so on. So the origin, what I want to say here is the origin of the sciences are the techniques. Okay, so let's move forward. And what do we understand about technology? In general, these philosophers, say that technology is a technique that uses or incorporates scientific knowledge, for instance, mathematics, for instance, physics, after the sciences have been configured. At the beginning, it was not obvious, at the beginning of the history of human being, but nowadays we can say that almost all techniques have become technology in developed countries, not in all the countries, but in developed countries. For instance, here, where I am now, in Spain, in the Basque Country, all the technology that we develop, we engineers, we use a lot of mathematics and so on. Let's see one example. For instance, in medical technology, there are scanners, X-rays, and etc. There are many technological devices. They are full of electromagnetism, chemistry, biology, and so on. In ship technology, for instance, in nowadays ships, for instance, in order to do the propeller, in order to design a proper efficient hull, the dynamic positioning of the ship itself is full of electromagnetism, chemistry, geometry, fluid dynamics, physics, and so on and so on. And finally, I would like to give an idea about what we understand of philosophy. There are many conceptions, there are many ideas of philosophy, but here, as I said before, I will follow this tendency, or the tendency given by these philosophers. And they say that the philosophy is a second degree of knowledge. Why? Because they say that the philosophy comes after techniques and science. So the philosophy needs the techniques and the science in order to analyze them. So basically, the philosophy is oriented to analyze, compare, discuss, and go further, etc., but always based on the knowledge given by sciences, techniques, and obviously technologies. There was a German philosopher and psychiatrist who was called Karl Jaspers, that he used to say that there is no escape from philosophy. We all do philosophy. The question is if we are doing good or bad philosophy. So in order to do good philosophy, what these people claim is that the philosophy should go further, but the sciences and techniques, but always based on their knowledge. I would like to emphasize here that technique, normally, we associate it to the human being, but I would like to say that obviously everybody knows that there are some animals that they also have developed techniques. Like, for instance, the beavers, castores in Spanish, you know that they create huge buildings or huge structures in the rivers and so on. And the technique developed by these animals and our techniques is not so different. There are many more examples. For instance, the termite nests, they build these structures in order to live them there. So they have elaborated a collective technology, a technology that is made collectively. Then, for instance, also in monkeys, the capuchin monkeys, they can use stones to break things or to take food from different elements, or even in birds, ravens, they are very clever and they can use sticks in order to take food from different elements, and so on and so on. So just focus or just emphasize that the technique is not unique for human beings, also appears in animals. But as far as we know, sciences, animals have not developed sciences like mathematics and so on, and therefore neither technology, neither philosophy. Okay, so let's continue with the presentation and let's go for this second part that maybe is the most difficult part, philosophy of technique. I will do a presentation, I will do a summary, in fact, of a presentation made by Luis Carlos Martín Jiménez almost 3 years ago now, entitled Philosophy of Techniques, Filosofía de la Técnica in Spanish, which is a teacher of philosophy. And full presentation and more information related to this philosophy of techniques can be found in this webpage. There you have some videos and so on. In this main source, it makes a summary and makes an analysis of the different philosophers and people that in general have been thinking and developing philosophic theories about technique. There have been many individuals, and what he makes is basically divide the propositions or the proposal made by these philosophers into 8 main models that we will see all of them, these 8 models. Then for English, in English also, I will recommend this book, which is a very long book, full of original texts related to people or related to philosophers speaking about technology, such as, for instance, Plato, Aristotle, Bacon, Kant, Heidegger, and so on and so on. And it has been edited by Scarf and Baldusek. Okay, so the first model about philosophy of techniques, we can say that they provide a negative view of the technique. And it's basically supported by Aristotle and the pre-Socratic philosophers. So it's a very old tradition, more than 2 millennia. It was developed more than 2 millennia ago. And this is a negative view of technique. They do not see technique in connection with science. They don't see these connections, this connection at all that I have been speaking about before. And they say that the technique is not connected with reality. The techniques deviates us from reality. So it degrades the idea of techniques and technicians. And they say that the technique is only understood as positive when we use it to imitate the nature in general. For instance, to imitate the songs of the birds and so on. And this view, that it is a very old view, is very common in philosophers and thinkers in general up to the 17th century, such as, for instance, Neoplatonism, scholastic philosophers, and so on. And we could say that nowadays some environmentalisms and ecologists view from nowadays, they can understood as an evolution of this view. The imitation of nature, they propose the fusion with the nature, to eat a lot of herbs and so on. It could be understood, maybe they don't know it, and they don't know it, but it could be understood as an evolution of this negative view of techniques founded in these people or philosophers. Then there is also a second model, a little bit different but very similar, with a view very similar to the previous one, to the model one. And they provide a degenerative view of techniques. They say that the technician is a servant, and it is very associated to Christian philosophers at Middle Age. We could even say that this model 2 is an evolution of this negative view of techniques, because we know that this philosopher influenced very much in Christianism, but here the novelty is that they include the God, the presence of God. And they say that the only one who creates is God. So the technician should be the most important thing. That's why they view as the technician as a negative or degenerative concept. Here again, they do not see that the connection between the science and techniques, and it is again common until 15th century, but however, this view also starts to change through Christian thinkers or philosophers, like such, for instance, Nicholas of Cues and some others. So these are the first two models that we are presenting. Model 3 now starts to have a positive view of techniques. Now they don't see techniques as negative, but they see technique as something positive. And with Francis Bacon mainly, but also there are some other philosophers such as Paolo Rossi, Juan Luis Vives, Galileo, and so on. So they dilute the idea of science and says that techniques is the truth. Therefore, this idea is not in contact with science, because they deviate the science, they put at a lower level the science, and they say that the technique is the only truth. So they say that printing, compacts, and gunpowder are technical inventions that dominate the world and are much more important than empires and anything else. Something in a very reduced way, in a very simplified way, we could say that this is what they say in the authors or philosophers related to this Model 3. Then we have Model 4, and the main idea of these philosophers is that technical inventions are organic projections of human being. Here we could emphasize, or we can highlight authors such as Scarf, McLuhan, Simondon, Serres, and so on. And this idea is very much related with the philosophy of the unconscious. So this is this philosophy, and the technique concept or the technique view is related to this philosophy. And they basically say, as the title says, that the human organs are projected in technique. Therefore, what they say is that all the inventions that we make are extensions of our body. So, for instance, here we have the digestive systems. From the digestive systems, we have created and we have generated the ovens, for instance. From our nervous systems, we have created, for instance, the electricity and all the devices related with the electricity. From our brain or from our mind, we have created the states, the governments, the nations, and so on. So, as you can see, this Model 4 is a very general and metaphoric or metaphysics idea of technique. It provides us a very metaphoric idea or general idea of technique. Okay, so let's move forward. And here we have Model 5 of technique, and this is a view in which they say that the technique presents its own life. Here we can emphasize authors like Jacques Ellul, Herbert Marcuse, Harman, and so on. And I will say, and I would like to focus or emphasize here as well, that from this Model 5 until Model 8, I will say that next models and this model, Technique, they see that the techniques is in connection and is very much related with the sciences. So techniques are to use sciences, not are starting, they use sciences, as I mentioned at the beginning of this presentation. And they say that the technique is autonomous, presents its own life and tries to survive and tries to get its own reproduction. So it is autonomous. And they say that the different societies that there are in the world nowadays are meshed in technical inventions. Again, in general, these are very metaphoric or general ideas and do not analyze techniques in their specificity. They give a very general idea and they say that everything related with techniques behaves in the same way, and they say that the techniques is almost a living entity. Okay, let's go now to Model 6, and in this model they see techniques as an opportunity or as an event. Here we have the very important philosopher, German philosopher Heidegger, and the idea of the being of Heidegger is realized through the technique. He says he connects his idea of being through the technique, with the technique, and says that the way of living of humans is based on technique. Not only technique, but technology as well. But here we are using the same pattern for all the exposition, technique, but sometimes we will mix technique with technology. However, modern technique and sciences, Heidegger sees the advances in biology and cybernetics that nowadays are very, very strong. So these advances, modern techniques and sciences, are going to hide the being, that idea of Heidegger. The being is going to be totally lost, and therefore human being is going to become as another object more. So the technique is going to be stronger than the human and than the being. So that's why it is an event. Now it is going to become more important technique rather than, or technique is going to become as another important element at the same level of human beings. Here also we have Spengler, that we could simplify it, say that presents very similar ideas to Heidegger, and he emphasized that we live in a magic world, which is in some way true, full of magic devices. 90%, 99% of the people depend on technical developments, and we absolutely do not know how they work. For instance, the smartphones, the internet, my car, all the devices that I have in my house, like for instance the fridge, the ovens, and so on and so on. I depend on these devices, and they are totally magic for me because most of the people do not know how they really work. And they also say some very general ideas, such as, for instance, this one here: the world nowadays is dominated by money and is sustained thanks to the democracy, and so on and so on. The democracy is being joined by the money, and the money again is taking so much power that is going to be, it's being more important in some cases than even the human beings. This is model 6. Again, in a very simplified way, but the main ideas are, I think, here. Then model 7, it is another idea for techniques, and they say that the technique is an orthopedia. And here we could distinguish authors such as Marx, Ortega y Gasset, Spanish philosopher, Bernard Stiegler, and so on. And they say they have a conceptual idea of human being as a degenerated fetus. It is weak. It is unable to do things autonomously. Depends on family and other people and so on. So, as we are like this, as we are weak, how do we solve this problem? By developing technique. So here they say basically that desire that we have, in general, all kind of desires of different natures for human being, come from our subconscious dissatisfactions. So we feel insecure and our problems are projected in others. Here I would like to say, and I would like to emphasize, that this is a different concept from Model 4. Because there in Model 4, the human conception is confident. We are capable of doing things, and we are able to overflow our limits, and therefore we create techniques. However, here the conception is that we are weak, and as we feel insecure, that's why we create technique. This is the main difference between these two models, I think. They say ideas, or they defend ideas such as, for instance, all our socializations are going to be made through technical objects, which is true, or not all, but many of them nowadays. Cinemas, social networks, and so on. And they say that techniques, some of them say that technique will give path to a new era. So here, again, we can conclude that this conceptual view of techniques is a very general or metaphoric concept or view, and their ideas do not tend to analyze techniques specifically under detail. So finally, we have Model 8, and here the main topic, or the main title, we could say that technique is dialectic. And here, this view, I think, is very close to the view of technique that we have engineers or people related to technology or technique in general. It comes from a very old philosopher, Plato, and for instance also to the philosopher I mentioned before, Gustavo Bueno, and his disciples. And they defend that techniques generate sciences. Obviously, not all of them, thanks to techniques, have been created by human beings, sciences, such as mathematics, astronomy, geography, and so on. And dialectics between techniques and sciences creates philosophy, as we mentioned before. So philosophy is a second degree of knowledge, not second degree because it's less, because it comes after technique and science and tries to go further. Techniques, in a sense, are different and can be distinguished one from each other. However, they are strongly interconnected with all types of links. Techniques can be specified, particularized, and they can be analyzed under detail. This is what they say. These general ideas or generalizations or simplifications, they are not agree with them. They could be true in some way, but what they say is that we need to analyze under detail the techniques. So they say that truth is in the pair of shores themselves, in the specific and detailed analysis of the techniques involved for doing the shows. So the truth of the techniques is in the shows, in the trousers or in the mobile phone. Truth, they say, is not a mental or generic conjectures or metaphoric explanations. These are simplifications. This is what they say. This model 8 accepts the previous models. They accept the truths. It says that in some specific cases they can be truth, but in many others they cannot be truth. They are not reflecting the reality as it says. They say that the reality is much more complex. Therefore, they propose to analyze all the specific techniques and understand the details of the context that they determine. These specific contexts are the only operating ones. There is an interesting presentation of the evolution of the techniques made by Luis Carlos Martín Jiménez, as I told you before, and he says how the techniques have been evolving. He makes a quite interesting essay showing how the techniques have been evolving, creating sciences, and from very past, from very old beginning, many millenniums ago until nowadays. Okay, so let's continue with the presentation, and let's go now for this third part of the tutorial about the need for models. I will now get closer to the wind turbine technology, but I will still be in a will make the presentation in a very general way. About the need for models. Let's see in one example of one offshore wind farm, which is here, composed by different wind turbines, connected all together by submarine cables. Then we have a high power transformer. Then we have one big submarine cable, and then we have the connection to the point of common coupling to the network or to the grid. Again, not always, but often by means of another transformer. So let's see how do we design a wind farm, nowadays at least. And I will defend the idea that we develop the wind farm and the different components composing the wind farm based on models. Okay, so as we have seen, there are different elements in the wind farm. Maybe the most important or the most typical or the most obvious one is the wind turbine. And you know, here you have a picture of a schematic of a wind turbine. There is a foundation that should be into the water or floating in the water. Then we have the tower. Then we have the nacelle. And then we have the blades. Normally, after evolution, we have seen that the three-blade system is nowadays at least the most efficient one and reliable one. Here we have the wind, so the wind creates some forces, some efforts at the blades, and this starts rotating. And in order to get or to capture this mechanical energy from the wind, we develop here an electromechanical system based on a generator in order to capture, as I said, the energy from the wind, from the mechanical movement created by the wind into the blades, into electrical energy by means of the generator, a power electronic converter, and then goes down through the transformer and through the electrical network, as we have said, or as we have seen before, through submarine cables in a wind farm offshore. So for the wind turbine, here we develop normally a model of the three-blade system. Here we have the energy flow going through the blades, and this rotates the blades and creates a mechanical energy. Then we transform it to electrical. So in order to model this phenomena, normally in electrical engineering we use quite simple formulas. We use quite simple equations based on obviously mathematics, because we use equations, and those formulas also are based on physics, fluid dynamics, aerodynamics, and so on. So here this could be our model of the three-blade system, this set of equations. However, often in order to simulate or in order to analyze into more details some specific phenomena, we could develop a three-blade system model, more complex, that integrates or considers more elements, such as, for instance, the shadow effect, the shear gradient effect, how the blade is affected by different wind speeds, and so on and so on. So obviously, if we go for this, if we want to consider this phenomena, these formulas or these equations are not enough, and we should develop a model which is more complex. But we are still using a model. If we analyze now this element, which is the mechanical system, the transmission system, that could be composed depending on the wind turbine that we are analyzing, based on the generator, rotor blade, the coupling, and so on. So here again, for the mechanical transmission system, again we have a model, and in the most simplified version is just consider that all this mechanical transmission system is just one inertia, very simplified model. And the equation that describes our mechanical transmission system will be this simple first order differential equation. So this will be our very simple model. Again, if we want to analyze it into more detail, we can go one step further, and we could consider damping factors between different masses, between the different axes rotating of different nature, physically different, therefore they have different inertia, they have their coupling, the coupling to the base of the wind turbine, and so on and so on. So if we consider all these issues or phenomena, we should develop a more complex set of equations, which means that we should develop a different model. So here again we have different abstraction levels for the model of the transmission or the mechanical transmission system, depending what we want to analyze. Let's move further and let's analyze now the generator. Again, with the generator we do something very similar. Depending on the topology of generator that we are using, here I have taken just one photo of a double feed induction generator, which is very popular in wind turbines. We normally analyze it by developing an equivalent electrical system, such as, for instance, this one in here, represented in alpha beta reference frame, and so on and so on. And by using complex space vector theory, we develop the voltage and current equations, which are magnitudes of the generator. So in that way, we can also develop flux equations, the torque equations, power equations, whatever we want. So this is our model. And in this way, by using these equations, we have the model and we can know which is the behavior of this generator system. And therefore, we could design better generators, or we could do any analysis that we want. So here again in the models, we are very much used, nowadays at least, to use models. Then we often have the power electronic converter. Here again we have a high power power electronic converter of this company, and within or inside the power electronic converter we know that we have the modulation, and again we can use different modulations, but those modulations are based on different type of models: space vector modulation, PWM modulation, and so on. Then we often, not always, not all the people is used to do that, but we often use converter models, the converter itself, that could be represented by some blocks. I don't want to go into details, just see a representation of a block diagram that represents the model of one converter. And the control that is normally implemented within this cabinet, in which to this element we call it converter and control. Sorry, I realize now that this is in Spanish, converter and control. Anyway, for the control again, we use different block diagrams, we use Laplace transformations, we use mathematical equations. Again, we are using models to know how behaves the elements within the converter, control, modulation, and so on. Outside the wind turbine, so we have seen that within the wind turbine we divide the different elements of the wind turbine: 3 blades, mechanical system, generator, converter, and so on, and we use different models. Outside the wind turbines, as we have said before, we have also transformers, and the transformer, again, the typical model that we develop to understand the transformer is based on a equivalent electrical system, such as for instance here, and from here we develop different mathematical equations. That could be the transformer that could be inside the wind turbine, and the big transformers that could be for the transmission system through the submarine cables and to the electrical network. Then we have also the submarine cables, and the submarine cables are also a very complex elements in which we have an equivalent electrical system, or we develop it in order to understand how it behaves, these cables, and depending the degree of accuracy that we want to obtain, we could consider just a simple resistance and inductance, or we could even consider the parasitic capacitances, or if we want to consider the variable frequency or the variable impedance through the frequency, we could also consider this Cauer-Foster networks. So at the end of the day, what we do is develop different mathematical expressions. Again, we are using different types of models to understand this. And many more models or more elements which are present in the offshore wind farm. Model for the wind itself, or for its prediction or forecast. Model of the AC grid or network to where we are going to be connected. Economic models to understand and to know how is the cost or the economic issues of the whole wind farm, the mechanical models of the blades, of the tower, of everything, many models. And normally the models that we use help us to do many things that could be simplifiedly said that they are used to be or to do analysis. And here we want to, I would like to speak a little bit deeper about models for analysis. So here now I have some few slides related to this content. And in general, we start, not always, but we start by using the analytical model. The analytical model is just a set of equations, of mathematical equations that describe the behavior of something. For instance, the generator, the wind turbine three-blade system, the mechanical system, anything that we want. We normally, as we are defending or we are saying in the previous slides, these mathematical equations that give us the analytical model are based on sciences such as, for instance, arithmetics, geometry, physics, reference frame transformations from fixed movings and so on, so more mathematics and geometry. We use in electrical engineering at least differential equations, and we use Laplace transformations, which are different tools or different tools provided by mathematicians. Then we apply harmonic decomposition, Fourier analysis in order to do different things. Then we use control theories, automatics, thermodynamics, fluid dynamics, and so on and so on. Then nowadays, in the last 10 years especially, we are used to use again a different type of models, which are the computer-based models. In this type of computer-based models, normally when we use them, we forget about the analytical model, about the mathematical equation describing, for instance, the behavior of a generator. And in this case, the computer-based model itself creates its own model. And we forget about the necessity to develop the model. So we simulate on it, and we see how the generator or whatever we are analyzing behaves. But we don't deal, or we don't need to create or to develop the mathematical equations of the element that we are analyzing. So this is a second level of abstraction, I would say. And here in engineering context, we could find software for numerical computing, software providing predefined models and toolboxes, such as, for instance, MATLAB, Simulink, and so on, Sabre, Pessim, Pescat, many of them, many commercial computer-based models. Software computing on the basis of finite element methods, and so on and so on. Then normally we develop, at least in some contexts, in university and companies, very often, experimental platforms in which we validate what we have developed or what we have designed by means of by the combination of the analytical model and the computer-based models. So in these experimental platforms, normally they are laboratories for testing and validation, general or specific aspects that often cannot be tested in the real system. Very often in these two types of models, or these two degrees of model, there are phenomena, there are realities that are not modeled, that are not considered, and that's why we generate these experimental platforms in order to see if these non-considered phenomena here will affect us considerably. So here we have fault generators, for instance, in wind turbines, for low voltage read-through, for another applications in railway tractions or whatever. Then here we have hardware in the loop that could be considered something which is in between these two circles of spheres. And finally, normally in engineering context, our objective should be to obtain the real system. The real system of the element that we are analyzing or designing or building. For instance, the wind turbine or the elevator or the ship or whatever it is. And here, again, we analyze and we see aspects that can be only found on the real system. Here there are many issues related to the work of the manufacturer and to the element itself. There are many limitations, there are many specific contexts connected to the real system or to the real product that we have developed, that is going to be later sold or implemented, I don't know where. So ideally, here we normally generate an iterative or recursive process of constant improvement. We go first here, then here, then here, then here, and again, if we see that something should be improved, maybe we come here or we come here, we change something and we improve, I don't know, for instance, the value of one specific filter in order to see or improve one problem that we have seen here or here. So this is a recursive process. Not always impossible, but it's possible, but depends on the context. But we normally work here, work like in here, I would say. Okay, so let's go further. And we could say that models can consider different degrees of realities or phenomena. And we will say that we have different abstraction levels or accuracy levels of models. For instance, in cables, as we are analyzing this element, and is a typical element which is present, which is always in all the electrical devices or technology, we could use a very simple model, for instance, composed by a resistive and inductive element. Or we could use a model 2, which is more complex than the previous ones and considers the parasitic capacitance of the cables. So in order to see phenomenon that appears at higher switching frequency, at higher frequencies, for instance, we should consider these capacitances. And if we want to go much more further and we want to focus on very, very specific and detailed phenomena, we could use a more complex model of the cable, such as here. And we consider the frequency dependency of the impedance of the whole system. So depending on what we want to do, we could move on different models in this element, for instance, of the cable. So we try to consider the more representative phenomena and can be useful often, not always, but often, to have different abstraction levels. So the more realistic phenomena that we consider, the better that we will describe the reality and better design we will make. Why? Because less uncertainties we will have, but obviously we will be dealing with more complex models. Let's see for some examples. For instance, a wind farm design not having into account the resonant behavior of the cables Probably, if you design the wind farm in that way and you don't consider this resonant behavior, you will have a problem after you build it up. Another example, a wind turbine design not having into account interaction between other wind turbines. If you don't model, if you don't study this phenomena, you will have a problem, probably. Or your design will be less efficient and reliable than the one that considers this phenomenon. A wind turbine that do not consider sudden wind variations. If your control strategy of the wind turbine is not prepared for wind variations, probably you will have some problems. Or, for instance, going into more specificity, wind turbine generator design not having into account the thermal stress of the generator, and so on and so on. So here I will also emphasize that the models that we integrate or that we develop should be integrative models that allow us to add partial or individual models. Therefore, we derive a global model that integrates all the individual models and is prepared to incorporate future individual models or individual models in order to incorporate future aspects that we haven't done before. Okay, so let's see this into more detail in next slides. And let's see it, for instance, with an example. So, for example, if we have a power electronic converter plus a cable model, and we want to model both elements, the power electronic converter with its control, modulator, filter, and so on, and then we want to connect it to a different element of totally different nature, such as, for instance, the cables of an AC grid. So here I have distinguished two individual elements, two separated elements. And how can we proceed? How can we model these two elements, power electronic converter and cable? So one strategy could be, for instance, to use a cable model with a certain degree of abstraction, and which is useful up to 2 colors. Or, depending what we want to do and what we want to study, we could go for a more complex model, as I showed you before, which is useful up to frequencies, for instance, of 5 kHz. Or if we want to go into many details because we want to analyze into many specific phenomena, we could use a much more complicated cable model, for instance, cable model 3. For the power electronic converter, for instance, we could do the same. We could have the same scenario. We could have a converter model 1, which does not contemplate the control loops. Or we could develop a much more complex converter model that contemplates the control loops. And finally, we could go further and contemplate or generate a model that takes into consideration delays and discretizations of the control of the power electronic converter. So we could have all these situations. I think you see the idea. Obviously, model of converter or cable 3 consider phenomena that model 2 or 1 does not consider. However, as a disadvantage, it is much more complex. So once we have the individual models with a certain degree of accuracy or of abstraction, call it as you want, we should develop the global model that develops or considers both individual models. This is a good methodology. The global model should be able to be modular, integrative in the sense that If we want to add another model, it should be easy to do it and reconfigurable. If we want to change and add another element, for instance, I don't know, the generator or the wind turbine model, it should be able, or it should be prepared to be reconfigurable. And also in the sense that if we want to change the accuracy of the cable by using a different model, it should be able to accept it, or to a more complex model, or to a more complex converter. This global model methodology that integrates these two models should be prepared for these changes. It is a very efficient and easy way to work. So once we have the models, how do we normally work? Normally we have some specifications given by codes or client, or by the cost that we want to, or the money that we want to spend in our product, or volume, or dimension restrictions. Anyway, we have different type of specifications. In order to meet these specifications, we develop different models of different abstraction levels with different data or parameters and so on. And finally, once we have the model, we do the analysis, or we do the study at different conditions. We compare different designs or with different parameters or data and so on. And we see, by means of the model and the analysis, if we meet the specifications. If we don't meet the specifications, so well, obviously we should change a parameter or even the model itself or something that we are analyzing until we meet the requirements or the specifications that we will finally end. So here the situation could be very different, very diverse. We could do this, we could follow this process by means of a very simple model, which is just an equation that gives us the resonant frequency of an AC grid. But we could have a different model, much more accurate, much more complex, to meet some other specifications and allow us to define the dynamic behavior of the system by means of the poles and zeros, and allow us to perform a simple tuning of regulators. So in order to do that, this analysis, we could develop this more complex model. That could be analytic or could be computer-based again. And if we want to go into many details, if we want to be very specific, we could develop a model 3, for instance, based on MATLAB simulating toolboxes, very under detail, and allow us to study the effect of the dead times of converters on the global power quality of the wind turbine or on the wind farm system, or whatever we want. So here we could have several situations to do design, and with this methodology we can say that we are providing tools for a more efficient and reliable design. Okay, so let's go now with the fourth part of the presentation, and I will do here a short history of wind turbines. And I will focus on the electric part of the wind turbines, on the history of wind turbines based on the electric part, basically on the electromagnetic conversion of energy. I will do this history, I will divide this history into two parts. Obviously, it's going to be very short, in less than 20 minutes probably. But first of all, I will do a general historical approach of the last centuries, and I will base on the very work very good work done by Professor Tabner on this book. And then I will do a second step of the historical evolution of the last 25 years of wind turbines. Always focus on the electrical parts. Okay, so let's go for the first part. And here we, starting from the beginning, that is very far away, we could say that before 200 years before Christ, wind machines were used in Persia. At least there is documentation or there are sources that say that. Then also at the 7th century, the first practical windmills in Persia for grinding grain and pumping water are found. These are very old designs, but it is curious that even nowadays in somewhere of today's Afghanistan and Iran, sorry, we can still find windmills with a similar structure to what we have in the 7th century. Then if we move forward, if we go to the 19th century at this year, we can say that the first automatically operated windmill for electricity production and for battery charging by Charles Brush in USA was made. It was 12 kilowatts. It was generated by means of a DC generator, and the wind turbine structure was 144 blades, the typical American wind turbine design. Some few years later, according to the sources, it is said that James Blyth in UK and Paul Lacour in Denmark, they built some innovative designs of wind turbine of 10 kilowatts with DC generators. Moving forward, we can say that during these years we could find several designs and several attempts of mixture of American and Danish designs of wind turbines. The power range was between 5 and 35 kilowatts, and there were some up and downs due to the First World War, and they suffered the competition with diesel engine in order to generate energy, so there were some up and downs for wind turbines. Then in the Soviet Union, and this year, it is found that a modern 3-blade wind turbine is built of 100 kilowatts and 100 meters height. It is connected to a 6.3 kilovolt distribution system, obviously by means of a transformer, and it can be see clear signs of aeronautical influence. 10 years later, in USA, the world's first megawatt height wind turbine is built, connected to the local electrical distribution system, which is something quite important. Here you have some numbers: 2.25 megawatts, 57 meters of diameter, 40 meters height, 2-blade design. It was a gear drive, so there was a gearbox, sorry. It was a constant speed electrical topology, and it was downwind, so the wind was coming through this way, from behind. So some authors, some historians say that this was the first modern wind turbine. Then, some years later, it is found also that in France some quite high power designs were made. They were geared with gearboxes, they had pitch control, they were downwind, and they were the interesting design, but not subsequent development was made, maybe because the French national decision to concentrate on nuclear power. Then here I don't have a photo, but during these years, the modern small-scale wind turbines between 1 and 10 kilowatts were starting to be created and developed. In Denmark, two strong designs were made of 200 kilowatts and 630 kilowatts with three-blade designs. They were geared with pitch control and one without pitch control. This was with pitch control and this was without. And they were again fixed speed topology from the electrical point of view. Some few years later in USA, several two-blade designs were made of different power with pitch control, but they result unreliable, mainly because some mechanical problems due to the structure of the two blades. But anyway. Then here, in these years in Germany, a 3 megawatts, which is this one, through-blade design was made. Fully rate cycloconverter was created, but it results unreliable. And in UK, this one, 1 megawatt 3-blade fixed speed design system was created, but it was maybe too early. It was simple and reliable, but there was lack of market. For that years, maybe it was too early. And in the last 20 or 25 years, we can say that we have been developing a huge amount of different type of wind turbine designs. Let's say that between 1 megawatt and nowadays we are starting to install 8 megawatts high power commercial wind turbines. They present pitch control in order to be efficient, direct drive or even gear drive. We can find several configurations with low voltage right through a grid called meeting, which is a very demanding and challenging issue. We can find wind turbines onshore, offshore, and so on. And from the generator point of view, we can find permanent magnet, double feed induction generator, a squirrel cage induction generator, bull rotor synchronous generator, a huge amount of different type of topologies of wind turbines, watching from different dimensions, watch it from different point of views, can be found nowadays, and they have been developed during these last 25 years. So now, in next slides, I will focus on this last 20 or 25 years development, historical development of wind turbines based on the electrical parts. So from the past, we will come in, or the dominant topology for the wind turbines was the fixed speed, squirrel cage induction generator. So here we have a very robust or reliable design of generator, and it was connected to the grid directly by means of a transformer, but without using power electronics. Okay, at the beginning maybe we use a soft starter, but then at the steady state this soft starter is switched and the generator is directly connected to the grid. So this is a direct connection of wind turbine. Then here between the three blades at the generator, in order to be efficient in the speeds, a gearbox is normally necessary. And finally here we put some capacitors in order to be efficient in the sense of the reactive power exchange with the grid. So this could be said that was the first design of wind turbine coming from the 90s. And here the main issues were the robustness and reliability of the wind turbines, but then the efficiency started to be important, and therefore we can say that a second family of wind turbines started to appear that was based on the boom rotor induction generator. And still use a very strong design of machine, but we are starting to put here a very simple power electronics, diodes and IGBTs combinations in order to achieve here a variable resistance, and in order to obtain here at the wind turbine rotational speed a short variation, higher than the one obtained here. And with this we obtain better efficiency. So during these years, at the beginning, the combination of these wind turbines were being installed in different parts of the world. These necessities were still there, but then as we started, or it started to appear, or even in the past they were there, but weight, volume, cost, and adaptability restrictions or requirements. And due to basically one advance of the power electronic technology that was developing or was making more robust and reliable the power electronics, I mean, in other contexts, such as for instance in railway, in ship propulsion, and so on, the variable wind turbine appeared, variable speed wind turbine appeared based on the double-feed induction generator. So here we use a double-feed induction generator and with a power electronic converter of a small scale. More or less 30% of the power of the wind turbine goes through the power electronic converter, and the rest, 70%, goes directly to the grid. So with this design, it becomes dominant during many years, even decades, 10 years, more than 10 years, and we obtain variable speed. However, depending on the locations, these wind turbine topologies were still being installed. Then later, or maybe earlier, I don't really have very clear, but in parallel there was another topology appear based on the squirrel cage induction generator, a very reliable design of generator, and it was variable speed, but the converter was of full capacity. So this design in principle was a little bit more expensive than the double-feed induction generator, but some of the designs, some of the wind turbines installed all around the world by some manufacturers were based on this wind turbine. After years, and once the number of wind turbines installed in the countries were making bigger, the dependency to these wind turbines or to the wind energy was bigger. Therefore, grid cost restrictions appeared, and they were more and more restrictive. And one of the restrictions, a very important restrictions, was the behavior during voltage dips. What it is called the low voltage read-through of the wind turbines. So the grid codes demanded to be robust to the faults at the grid, and the wind turbine should disconnect and should behave in a very specific way. So basically, due to this fact, appear or there were made some modifications in double-feed induction generator based wind turbines. That was the integration of a chopper or of a crowbar in order to be protected and in order to behave as demanded by the grid codes in these turbine topologies. In meantime, I don't know when, probably there were many actions. This is a simplified way of saying. There appear also the variable speed boom rotor synchronous generator and the variable speed permanent magnet synchronous generator, both using gearboxes. And this will be the configuration, again a full capacity converter, but the generator is different. And so here we could find with this general common topology different generators depending on the wind turbine manufacturer. In order to meet the grid codes, for these topologies as well, they included the chopper. So this initial design was evolved to this other one. And then somewhere in the time, not at the same time, but there were made different actions to obtain this same philosophy of wind turbine, but avoiding the gearbox by making a design of direct drive, which is this one. So eliminating here the direct drive, but in that case the design of the machine, and it should be synchronous generator, would be much more complex because it should work efficiently at low speed and high torques and so on. So that was another tendency. So as you can see here, there are many options, there are many topologies made by different requirements coming from different parts. And here as well we could say another dimension in which there were several developments in power electronics due to links with another technologies in railway or ship propulsion or elevators or whatever, and the same in permanent magnets. This technology was included or was introduced also to the wind turbines. Then also some other synchronous generator based on permanent magnets were made in order to reduce the cost of the rotor side power electronic converter, use diodes and only one IGBTs. A different configuration based on same generators but with different conversion system. Then, in order to reduce the cost of the wind turbine and in order to put the wind turbines at sea, to do offshore wind turbines, due to these requirements, higher power wind turbines were created, and here again different direction of different topology options were followed. One could be, for instance, parallelization of converters, very simply, as in here. You have one converter design, and if you want to go to the double or 3 times the power, you just parallelize the same converter system and you increase the power of the induction generator design. Here we have another branch. Another tendency was to use same converters again, but with different windings at the stator. Here the complexity of the machine is bigger, but there was another tendency. Or another tendency is to use the same converters on the same generators, but put the complexity in order to go to a higher power at the mechanical part at the gearbox by means of a distributed gearbox. There are different tendencies, different branches. Or even parallelizing this topology in this way, with only two windings and put parallel connections like in interleaving and so on and so on. So these many branches has result on the many configurations of wind turbines that we can find nowadays. They are coming from real necessities, real requirements, and interaction with other technologies or other advances in some other contexts. In the past, maybe this topology, this double feed induction generator topology with crowbar or chopper was dominant, basically because it was reliable and it was not it was the best option in terms of the cost. But nowadays, in higher power designs and for offshore, maybe permanent magnets or ship-based or wind turbines based on synchronous generators are starting to be at the same level or even more than this design. In the world will come more restrictions, be more efficient, be more reliable, and more restrictions. So this tree full of branches showing the technology at wind turbines will become more complex, or who knows. Okay, so after watching the history of wind turbines and watching that it has been conditioned by real needs and a specific context created by the wind turbine technology itself and some other technologies interacting one with each other, I'm going to try to give an answer to this difficult question, which is best electric technology in wind turbines. Let's see what happens. So for a given technology, we should analyze its performance at different dimensions. To give an answer to this question, we should analyze different what is better from a different point of views. So traditionally, reliability and availability concepts or demands have been very often demanded to wind turbine technology. So here, depending on the topology that we use, we could say that if we use a double feed induction generator, it has been said that the brushes of the machine itself is not good for reliability. However, after several years of working in proper conditions, it has been demonstrated that although, or despite the fact that they need maintenance, it's a reliable configuration. Then in the past as well, when the permanent magnets started to be implemented, there was the uncertainty whether they were going to be reliable or not. Nowadays, designs of this generator with permanent magnets, it's been watched, it's been demonstrated by evidences that they work well. So this is also a difficult issue to analyze, but it can be analyzed. For instance, if we use a converter, a power electronic converter that is composed by many parts, by many different and individually divided parts, we could say as well that from the point of view of the reliability, is not so good, but it depends. Also depending on, yes, if we use a gearbox If we use a topology of wind turbine, not direct drive, if we use a gearbox between the three blades and the generator. Some years ago, the reputation of the gearboxes was not so good, but again, the reality has been demonstrated by experiences of many wind turbines among many years and different manufacturers. It has been seen that reliability is good. Then we have also another vector or another requirement that could be grid code fulfillments. Grid code fulfillments are getting stronger and stronger during the time, since the dependency that we have for this wind turbine technology is bigger. So it has really sense this tendency. Here in the past, maybe the double feed induction generator, there were some years in which it was the most effective and less costly solution, but now with the low voltage read-through and the high voltage read-through requirements getting stronger and stronger, it has to be demonstrated that in the future is going to be the double feed induction generator a good solutions compared, for instance, with the full converter topology with with synchronous generator, for instance, with permanent magnets. That's the debate, that's the main question. Another vector or another issue that has to be taken into account is the efficiency, or if we want also the power, that both are much interrelated. So the bigger is the power from the converter point of view. If we use a full-scale wind turbine, the power electronic converter will be more expensive and more complex. So in that sense, the double feed induction generator maybe is in a better position because it's 30% of that power. However, it depends how much power we are. It doesn't. It's not the same if we are in 8 megawatts, or if we are in 5 megawatts, or if we are in 2 megawatts. Maybe the context will be different. Yes. Another vector or another factor that should be evaluated and analyzed in detail is the complexity at all the levels of the technology that we are using. For instance, some manufacturers tend to don't incorporate very complex control strategies because maybe the engineers that they develop the software and the algorithms, they can do it properly, they can understand the algorithm, but maybe in the coming years, the following engineers will need a lot of time to understand these complex algorithms, so they prefer to use simpler algorithms, but more easy to understand by all the engineers that are expected to be working in the wind turbine technology during years. So there are many factors related also to the complexity. For instance, maybe another typical example is that you design an output filter of the converter to connect it to the grid. You define, for instance, a filter in which the capacitance is one value, and then you go to the manufacturers of the capacitance and you need to put for instance 10 capacitance in series and in parallel in order to obtain the value that you want. Therefore, the reliability and the complexity of your filter that was supposed to be something very simple becomes complex. So all those factors affecting to this main factor or vector should be also very well analyzed. What else? Volume and weight. For instance, if we are using direct drive based on synchronous generator with multiple design, maybe the tendency of the generator is to be a big diameter, a long diameter. Therefore, the nacelle of the wind turbine should be or given specific dimensions. So these are requirements that has to be fixed with the surrounding technology or elements in the wind turbine. And many more examples. Maintenance and useful life, that depends on how the electronic devices and the electric generator and so on are made by the manufacturer, and that depends on many other factors as well. Temperature performance, the tendency also nowadays is to put more power in less volume. So the big issue, or one of the big issues, is to be able to evacuate the temperature, the big temperatures outside the generator, the converter, or whatever it is. So this is also another factor that maybe is not in accordance to this other factor, or to this other factor, or to this other factor. Oh, sorry. Then the patents and possibility to protect, which is just the opposite. Maybe you want to use one proven technology, for instance, I don't know, the DC chopper at the double feed induction generator for low voltage read-through, but you cannot do it because there is another company that is protecting that element in some specific countries. So therefore, you need to do something. So these are factors that has to be also taken into account. And just the opposite, if you develop a new technology, it's good if you can protect yourself, at least for some markets, for some countries, by means of patents. Another very, very important factor is the cost, obviously, and very, very important and very determining factor. But the cost as well is another multidimensional analysis. It depends of the manufacturing processes, the investments that you have to do, depending on the country where you are producing or where you are designing, the engineers and so on, the subsidies, the financial cost, the electricity cost. There are many factors here as well. And this is also, nowadays, we all know that this is very important. Again, this is a contextual factor, depending where you are localized, and the suppliers that you can use, and the people that you can use, or the workers that you can use. That are factors that maybe makes more complex or more expensive to use one technology or one solution than other. Another contextual factor is the historical conditioning and the preferences of the manufacturer. Depending on your experience, if you have started, for instance, with a synchronous generator, with a full-scale converter, and you have been working with that solution, it is very hard to go to another technology which is different. It is harder. So the historical conditioning also depends or influences quite strong in order to do improvements, for instance, in this direction, or in this direction, or in this direction, and so on and so on. Nowadays also it is becoming very important in many countries at least to be environmentally friendly. That's another factor, very important. Then also as well the working conditions of manufacturers, workers, engineers, and so on. It's not good to be for a company changing of technology, demanding a lot of efforts and a lot of energy for the engineers or workers in long term. It will cause difficulties. So that's another factor that should be taken into consideration when you do improvements in any of these directions that we are telling. Adaptability to different scenarios. If you are a company that your tendency or your philosophy is to adapt to every single customer that you are working with, so maybe you will have a very demanding scenario. Reputation as well. Maybe you don't want to take a lot of risks, therefore you don't follow many tendencies, or you avoid to use some specific some specific solutions for some of those requirements, and so on. Differential factors against others. There are some companies that they want to have, for instance, as a differential factor, the control strategy that they use, or I don't know, the capacity to work without transformer. There are some other, or with a transformer which is smaller in the wind turbine. There are some companies that try to find that kind of differential factors. And the market position also depends where you are. If you are in a good position historically, obviously that will be good for the future. But if you are in a less good position, to take advantage to those better positions will be harder. So depending at this specific moment that you are going to do the change or the adaptation to a new technology, it depends a lot where you are, which is your position at this specific moment. So depending on the company, you should evaluate each of those factors, and you get a spider chart that has this shape. This is a general case, and depending on the company, maybe for the same product, for the same wind turbine, based on the same dominant technology, maybe the spider chart or this structure will be different. And I would like to emphasize that all these dimensions or requirements or vectors of different amplitude that I have represented here in some way are in conflict all together, one with each other. Obviously the cost is in conflict with the, I don't know, working conditions of the manufacturers, or with being environmentally friendly, and so on and so on and so on. So finally, we can conclude that to find out the best solution is a very complex multidimensional analysis. The weight of each dimension strongly depends on each specific manufacturer, context, and history. However, despite the fact links are strong, factors change quickly and it's a hard work to do. Evaluation can be done and must be done. So it can be known in one specific context of one specific manufacturer, taking into account his history, his experience, his position, and so on. The best wind turbine technology can be done. And also it should be taking into consideration the projection to the future, how the market is going to be changed. Therefore, due to different initial actions taken by companies and the course of events, Nowadays, diversification occurs and different wind turbines technologies coexist. So for instance, for one specific technology of wind turbine or one manufacturer, we could have an spider chart very symmetrical, or for a different manufacturer, we will have a different wind turbine technology, or maybe the same, but with a different spider chart. For a different technology of a different manufacturer, or the same technology, it doesn't matter, maybe we have a different spider chart in which the vectors that he makes more important are different from this one or from this one, etc., etc., and etc. So all these technologies are in competitions one with each other. Okay, so let's conclude with this presentation, giving just some few numbers about the importance, or giving importance to technology, more specifically to the technology of wind turbines. So wind energy numbers at January of 2008, which is today, I will show you just four general tendencies, because there are many numbers, there are many statistics, but I think that with four main tendencies, it's enough to understand how it works. The wind turbine. The biggest wind turbine that has been created is, in the last 25 years, it has been increasing. Nowadays, the biggest one is 8 megawatts, and the diameter is around 160 meters. Obviously, not all the wind turbines that are installed every year are of the biggest one. There are also installed of smaller power wind turbines, depending on the country, depending on the locations, depending on the needs, and different manufacturers and different technologies. But the tendency of the biggest wind turbine every year has been increasing always. In the same direction, with the same tendency, here we have another two factors. Installed average power wind turbine and average power of a wind farm. So they are always going up, they are always increasing. The average power of all the wind turbines is installed every year, and the power of the wind farms. Nowadays, I think that 5 megawatts is the average wind turbine power for offshore, and 500 megawatts is the average size of the wind farm. Again, depending on the country, location, and so on, the actual values will be different, but the median or average values are these ones. And always in the last 20 years, this has been in an increasing tendency. Then the cost goes just in the opposite direction. In function of the power mainly, so the bigger is the power of the wind turbine and the bigger is the power of the wind farm, in general, the cost is smaller. And year after year, this is not so obvious, but I think that year after year also the technology, more mature technology, and also because the power and the average is going bigger, the average power is going bigger, the cost every year has been going down. So bigger power, bigger wind farms, bigger wind turbines, less costs. And finally, this gives us a fact that the installed power all around the world has been increasing every year. Depending on the year, maybe in one country is more than in others, but always in total, cumulative power installed all around the world has been increasing. Nowadays, I think that we have 500 gigawatts, and in European Union we have 160 gigawatts, 12% of the total power in European Union of power installed. And 12% more or less is also covered by the wind turbines of the total demand, which is roughly the typical number that is given 123 millions of houses. Then another number, one thing is the installed power in wind energy power, but then also what is different, as the wind is different depending on the place or the location of the wind farm. It is different how much is consumed or it's provided or is generated. So numbers say that in February of 2017 of last year, there was a record of around 70 gigawatts of power provided by wind energy. So finally, just some numbers. It seems that 637 is what in 2016 wind power avoided of emissions globally. I don't know if this number is very well calculated. I guess that this should be an estimation. There will be an uncertainty there, but I think that it's obvious that the emissions are reduced thanks to the wind energy technology. 341,000 wind turbines are installed around the world by the end of 2016, which is a big number. 8,000 is the number of parts that a wind turbine has. So a wind turbine is a very complex element composed by 8,000 elements. And this makes that we have more than 1 million of jobs created by the wind industry in 2016. In Europe, 500,000 people is the number of people expected to be employed by the wind industry in 2020. Okay, I guess these are estimated numbers, but they give us an idea, general idea of how important it is for us. And technology in general, if we go further, is very important, and we have many more global examples. For instance, transportation systems that have changed our lives, as well as internet or smartphones or social networks. All of those elements are technology, and they have become very, very important in our lives. So that was all. I hope it was interesting for you, this tutorial, and thank you very much for your attention.